Hello students, this video is for the Chapter 2 multiple choice review. We're going to be going over questions that deal with the normal distribution, with z-scores, with area under the curve, with the empirical rule, all those kinds of things. First, let's take a look at the correct answers. You can pause the video now to try and capture these correct answers and see how you did. And then once you figure out whether you did well or poorly on any individual question, you can skip to that individual question during the video. All right, let's take a look at the actual questions. In this first question, it tells us that Jorge's score on exam 1 was at the 64th percentile of the scores. That, of course, means that 64% of scores were below that. So it tells us, or it asks us rather, where his score falls. And it talks about the minimum, the first quartile, the median, the third quartile, the maximum, and it also refers to the mean. Let's take a look at where the 64th percentile would be. Well, here we see a normal curve, and we know that the mean and the median in a symmetric distribution are going to be at the same place. They're going to be at the center of that distribution, the peak. We know that that is the 50th percentile because that means that 50% of the data lies below that value. All right, so the 64th percentile must be a little bit higher than that. Keep in mind that the 64th percentile is going to probably be somewhere in this range here. So that 64% of the data is below it. Well, keep in mind that the 64th percentile is going to be higher than the 50th percentile, so it's going to be here. But remember that we're talking about quartiles now, the first quartile, the third quartile, and each of these has a percentile that it belongs to. For example, the first quartile is the 25th percentile, and the third quartile is the 75th percentile. Well, it stands to reason that the 64th percentile would be in between the 50th percentile, which we know as the mean or the median, and the third quartile, which is the 75th percentile. We're not really talking about at the mean score for all students, because if it was at the mean score for all students, it would be at the 50th percentile. I think for sure between the median and the third quartile would be the correct answer, because 64 is in between 50% and 75%. Easy. For number 2, scores on the ACT follow a bell-shaped distribution. Read asymmetric normal distribution with mean 18 and standard deviation of 6. The standardized score was negative 0.7, which means that negative is below the mean. So we can look through and say, well, if the mean is 18 and his standardized score was negative, that means we can instantly cut out anything that was above the mean. So it's definitely not this. And the standard deviation is 6. Well, it looks like we're going to have to pull out our z-score calculator, or rather just the formula for z-scores. And we know that Wayne's standardized score was negative 0.7, so that is the z-score, so that goes with that. We also know that the mean is 18, so that goes with that. The standard deviation is 6, so that goes with that. So it seems like all we're doing is substituting values into this z formula to find the value of x. Long story short, if you solve for x, you should get 13.8. Hopefully you got that. That's some basic algebra. George has an average bowling score of 180, and he bowls in a league where the average for all bowlers is 150. Oh, here we go. So we have an x value, and we have a mean, the average or the mean, right? Standard deviation is 20. How about that? Now we're comparing George, the first person, to Bill, a second person. This second person has an average bowling score of 190, so his individual score is higher than George's. However, his league is better. His league is 160, not 150, and the standard deviation is 15. This is where the z-score really shines. We're going to be using the z-score to compare two different values in two different distributions. So we're going to try to figure out who ranks higher in the league. In other words, who has a higher rank relative to his league. So here we've calculated the standardized scores, in other words, the z-scores of both George and Bill. George is going to be 1.5 and Bill is going to be 2. That means that Bill is better than his competitors than George is versus his competitors. So let's go through the correct or the possible answer choices. We know the answer is not going to be George, it's going to be Bill. Bill's higher. So we're going to cut off everything that says George. So it's not this one, it's not this one, it's not this one. So it's either going to be 190 is higher than 180 or standardized score is higher than George. While this is true, 190 is higher than 180, we're talking about in his own league as compared to the rest of the league. So we're using a standardized score. Beautiful. Number 4, if 30 is added to every observation in a data set, only one of the following that is not changed is, well, you know that when you add values to observations in a data set, that means that measures of center are going to be affected, and measures of spread are not going to be affected. Some of these things are not either, actually. There's the 75th percentile, and there's the minimum. Both of those are values in the distribution. So if a 30 is added to every observation, every value in the distribution, it stands to reason that the 75th percentile and the minimum would also be raised by 30. So those would change. Like I said, the mean and the median are both measures of center. So those would change. The only one that won't change based on an addition is a measure of spread. It doesn't change how far apart the values are spread. It just changes the center where they are located around. For number 5, if every observation in the data set is multiplied by 10, now we're talking about multiplication. Remember that multiplication does change values of spread or measures of spread. The only one of the following that is not multiplied by 10. Okay, the thing that we're looking for is a value that is not multiplied by 10. And if you remember, all of the measures of center and all of the measures of spread are supposed to be multiplied by 10. So the mean, that's out. The median, that's also out. Those are both measures of center. The IQR, that's a measure of spread, so that's out. The standard deviation, that one's out. The only one left is variance, and there's a reason for it. I know that variance is a sort of measure of spread. However, remember that the variance is equal to the standard deviation squared. So that means if the standard deviation is multiplied by 10, the variance is actually going to be multiplied by 10 squared. It's not going to be multiplied by 10. It's not the same exact change that happens to every observation in the data set. So since the variance is a different measure of spread than the others, variance is your correct answer. Let's look at question number 6. It talks about which one is least likely to have a normal distribution. Remember that normal distribution is the one that kind of looks like this. It's a symmetric bell curve. Let's take a look at each of these individual data sets. Let's eliminate some of the ones that are normal by design. You know that SAT scores are generally going to be normal because we have most people that are average. There are going to be some people that score exceptionally high and some people that score exceptionally low, but they're all grouped around the same value. IQ scores are also a traditional number that is considered to be normally distributed. Another thing that we consider to be normally distributed is height of all female students. You know that in general, people are going to be of quote-unquote average height. There's going to be some people that are abnormally tall, perhaps people that are on the basketball team or something else like that. And there are going to be people that are abnormally short, but regardless of that, those heights should be normally distributed. However, when you talk about family incomes of all students taking Stat 001 at State Tech University, you should consider that there are going to be some families that earn significantly more than the average. So let's say the average income of families that are attending, or families of students attending a university. Well, according to the U.S. Census, I just looked it up, they use 2 different surveys to try to figure out what the average household income is. And according to one of them, it's $63,000, and according to one of them, it's $61,900. So very, very close to each other. About $61,000 or $62,000. So that's going to be here. That's $62,000 value. If it's going to be a normal distribution, then that means there should be symmetric distribution going off to the sides either way. So that means it's possible that some people are around here, perhaps near the the poverty line, and some people should be over here. However, it should stand to reason to you that there are going to be way more people that are out here in this end than this end. From here to here, from here, that's $62,000 to the absolute zero of this curve, that's only $62,000. But if you add $62,000 to this, you're going to get to, $124,000? There are many, many families in the United States earning significantly more than that. So there's going to be a lot more numbers over here. As a matter of fact, I don't think I would be able to model this with a normal distribution. It would probably look more like this. It would probably look more like a tail right, skew right distribution, with most of the incomes being here, but there being some significant outliers to the right. So the correct answer is family incomes are probably not going to have that normal distribution that we're looking for. For questions 7 through 9, we're taking a look at this setting, and this is the normal curve for the distribution of weights. We're asking about what point C on the normal curve is. Point C is down here, and it looks like it is 1 standard deviation below the mean, so we'll label this as mean minus 1 standard deviation. It says in the problem that the mean is 80 grams and the standard deviation is 2 grams. So 1 standard deviation below the mean means 80 minus 2. That should be 78. Fantastic. The next question asks us about what percent of the cockroaches have weights between 76 and 84 grams. I know that the mean here is 80, so this is 78, which means one standard deviation below. This one is 76, so we'll label this as 76. And it's looking for 84, which is 4 above 80, which means 2, 4. This is 80. It turns out that we know something about 2 standard deviations below and 2 standard deviations above. According to the so-called empirical rule, 95% of our data should be between 2 standard deviations from the mean, 2 standard deviations below and 2 standard deviations above. So we should be looking at 95% of those cockroaches. Yuck, disgusting. Anyway, about what percent of the cockroaches have weights that are less than 78 grams? Well, remember we had 78 here. The 78 was labeled at mean minus 1 standard deviation. And we can figure out what the percentage below that is by remembering the other values in the empirical rule. I just redrew this a little bit to represent 68%, 95%, and 99.7%. What I'm going to do now is fill in all of these different spaces in the normal distribution in the normal curve to represent what percentage goes in each of the spaces. Since the distribution is symmetrical, that means that 34% and 34% respectively make up that 68% in the middle. Now we need to figure out how to get to that 95%, which means 95 subtract 68 and then cut that in half to get the area here and the area here, just like we did in class. That means 13.5% lies here and 13.5% lies here. Now we're going to do the same trick, 99.7 minus 95, and then cut that in half to figure out the space between A and B and the space between F and G. And keep in mind, this isn't all of the percentage, right? 99.7% lies within 3 standard deviations of the mean, but there's still 0.3% that is below A and above G. So what I want to do now is sort of interpret what we're trying to find. The question is saying about what percent of the cockroaches have weights less than 78 grams. So 78 grams is here at this red mark. We know that. 80 is here, which means 78 is here. So I could try to add up the percentages below here, or what I could do is say, well, I know that 50% of the data lies to the left of D and to the right of D, respectively. That means if 50% is below D, then I can take away 34%, which is not in that shaded region, and try to figure out what is in that shaded region, which is 50 minus 34. That should just be 16%. So, correct answer, 16%. Cool. All right, get out of the way, calculator. Let's keep going. Number 10, the proportion of observations from a standard normal distribution with values less than 1.5 is. Well, let's see. Let's break this down into what it's actually asking for. The proportion of observations. Okay, they made that a lot more difficult than it had to be. Proportion of observations, in other words, area under the curve. Not bad. The area under the curve from a standard normal distribution. We know that a standard normal distribution is a normal distribution with some very specific values. The standard normal distribution has a mean, which is equal to 0, and the standard deviation, which is equal to 1. And we're looking for values less than 1.15. So that means starting at 1.15 and going underneath that. If we do a quick sketch of the normal curve, I've drawn better. The proportion of observations from a standard normal distribution with values less than 1.15, keep in mind that 1.15 is probably going to be about here. We're looking for less than that. So we can easily, looks like I got rid of that calculator a little preemptively, we can easily use the calculator to figure this out. Let's bring the calculator back. So what I'm going to do is use the normal CDF, which is under distributions. I'm going to go down to normal CDF, and now your calculator may be one of those newfangled fancy ones that has all sorts of different prompts here, but mine isn't, so I'm just going to have to fill in what I know. The normal CDF uses 4 different arguments. The first argument is going to be the lower bound. In this case, the lower bound goes all the way down to negative infinity, but there's no negative infinity button on the calculator, so I'm going to use negative 10 to the 99th power. The upper bound is going to be the value that we're supposed to stop at. It tells us we're looking for all the values less than 1.15, so once we get to 1.15, we're going to stop. So 1.15. 1.15. Now, I know that the next 2 arguments are going to be the mean and the standard deviation, and I'm going to put in 0 and 1 because that's what you really should be doing. Every time you should put in your mean and your standard deviation. But I want you to know that the normal CDF actually assumes that you're talking about a standard normal distribution unless you specifically tell it otherwise. So if I were to fill in that exact same information, that negative 10 to the 99th and 1.15, the calculator just assumes that it's going to be a normal distribution because it gives us the same exact values. So that's a little piece of information to keep in your back pocket. Normal CDF assumes it's standard normal distribution unless you tell it different values for the mean and the standard deviation. Anyways, 87.49 is going to be my correct answer. Of course, that's 87.49%, which translates to 0.8749. Fantastic. Looking at the next one, the proportion of observations, remember that's just area under the curve, from a standard normal distribution with values larger than negative 0.75. Oh boy, it's like I'm seeing this all over again. I'm experiencing deja vu. Larger than negative 0.75. If this is the mean here, negative 0.75 is going to be about here. Values larger than that, which means I'm going to shade this way. That means I'm going to use normal CDF yet again. And for this case, I have a lower bound of negative 0.75 and an upper bound of positive infinity. So that's why I put in negative 0.75 as my lower bound, and then 10 to the 99th, which is essentially positive infinity. And I did put in the 0 and the 1, and I know you might think to yourself, why is he filling that in? It's not necessary when it's a standard normal distribution. Here's the thing. If I always fill in the mean and I always fill in the standard deviation, I'm never going to make a mistake. I always have to know the answers to these questions regardless of whether it's going to be a standard normal distribution like it says here, or if it's going to be normal distribution with a mean and a standard deviation that they give me. Might as well fill it in. It takes you literally 1 more second to do. 0.7734 looks like with the rounding, and 0.7734 it is. All right, let's clear this for a moment and take a look at question number 12. Many professional schools require applicants to take a standardized test. Suppose that 1,000 students take such a test, and then several weeks after the test, Pete receives his score report. He got a 63. That's maybe not so great, but it places him at the 73rd percentile, which means his is higher than 73% of other students. This means that, oh, wait, it's just literally asking about percentiles? Great. That means that he scored better than about 73% of the test takers. That's literally the definition of percentiles. Definition for your knowledge is a value below which a certain percentage of data falls. So that means 73% of the people who took this standardized test got a 63 or below. Moving on up. Question number 13 for the normal distribution shown. The standard deviation is closest to, well, let's see. We can easily identify one thing. Let's identify the mean. That mean is going to be right around here. Let's use my straight line tool to draw directly down to it. It looks like it's going to be about 2. Now, one thing that you should remember is that the first standard deviation away from the mean, either below or above, exists at something called the inflection point, where the normal curve changes concavity. In other words, from here downwards, we're going down, 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 and our slope starts at 0, but the slope is changing constantly as we go from here downwards. In fact, that slope is going from 0 to much, much higher numbers, right? It's getting steeper here, it's getting much steeper here, but somewhere in here, we can tell that it starts going back downwards. The slope starts decreasing again. So there's a point at which the slope stops getting higher and starts getting lower. It starts decreasing again. So that concavity shift looks like it's happening about here, where the slope stops increasing in height and starts decreasing in height. There's another point over here, and as you know, since it's a normal curve, it's symmetrical, so it should be around here, where the concavity shifts again. Here I'm going from a 0 slope to a much more negative number as it goes forward, but now from here onwards, that slope starts changing in the other direction. So it looks like if I trace downwards, I'm just about at -2, and if I trace downwards here, I'm just about at 6. That means the first standard deviation is at 6 and -2 respectively, which is about 4 units away from the mean. Fantastic. Now, I do want to keep in mind, I do want to warn you about this. This is not the type of problem that you would probably see on the AP exam, and you probably wouldn't see this on the test either. This is just making sure that people understand, that students understand, that the first standard deviation exists at an inflection point, which is where the normal curve changes concavity. This is a little bit more subjective than they typically are, the questions typically are, but just be prepared for maybe a definition about concavity change. For question number 14, rainwater is collected in water collectors at 30 different sites. They measure the acidity, the pH, and they give you the mean, and they give you the standard deviation. Great. unfortunately, those numbers are in error. The error can be corrected by adding, we're adding numbers to the distribution, and then multiplying the distribution by a number. Now, you should remember that multiplying and adding affect the mean and standard deviation differently. Specifically, that the mean is affected by both multiplication and addition of the individual values, but standard deviation is only affected by multiplication. The spread isn't changed by sliding the curve. The spread is changed by widening the curve, which would happen if you multiplied everything. So it looks like we need to do some math here. To the 4.60, we're going to be adding and also multiplying. To the 1.10, which is the standard deviation, we're only going to be multiplying. And if you thought that wasn't tricky enough, they also threw one more little curveball in here. It says the error can be corrected by, let's read it very carefully, first adding 0.1 pH to all the values and then multiplying the result by 1.2. We're not even going by the order of operations here. We do adding first, then multiplying. So you got to be careful to do that, because if you multiply first, then add, like the order of operations would sort of suggest to you, then you get the wrong answer. The mean, therefore, is the original mean, the 4.6, plus 0.1, that's what it asks us to do, add 0.1, and then multiply by 1.2. Answer should be 5.64, which means we can get rid of a lot of these potential answers. And then the standard deviation is 1.10. I'm only multiplying by 1.2 because any adding or subtracting is not going to affect the standard deviation, but multiplying by 1.2 does affect the standard deviation. 5.64 and 1.32, boom. Question 15, this is a cumulative relative frequency graph, but of course you and I know it as a percentile graph of the number of ounces of alcohol consumed in a week in a sample of 150 adults. About what percent of these adults consume between 4 and 8 ounces per week? Okay, well, between 4 and 8 ounces per week. These aren't the straightest lines in the world, but that's okay, because we just have to be a little bit accurate. If we go across, it looks like we're just about 60, and if we go across here, we're just about at 20. So about what percent of these adults consume between 4 and 8 ounces per week? It's going to be between 60 and 20. That seems to be 40% to me. Easy does it. All right, question number 16 asks about the very real location of Chillyville. The normal distribution, it pertains to their snowfall with a mean of 55 inches. Doesn't give the standard deviation, but that's okay. If the snowfall in Chillyville exceeds 60 inches in 15% of the years, what is the standard deviation? Okay, let's try to figure this out by looking at a normal distribution. Here's the normal distribution. Here's the snow in Chillyville. Oh, so chilly. And what we're able to do is draw at least one line on this normal distribution. We know that the mean is going to be 55 inches. Now, like I said before, we do not know the standard deviation, but it says the snowfall in Chillyville exceeds 60 inches. So let's put another line for 60 inches. So it says it exceeds 60 inches in 15% of the year. So that means let's shade this portion, which is exceeding 60 inches, and let's label it as 15%. Now, since we're working with a percentage that's given to us, normally what we would do is use Invnorm, and we're definitely going to use Invnorm in this case. However, we have to be really careful with how Invnorm actually works. Remember that Invnorm takes a percentage that we put into the calculator, and it spits out where that percentage either starts or ends. But if you remember from our discussion of Invnorm, Invnorm only works for at or below. It doesn't work for above. So in order to use Invnorm in this case, what we're going to do is not use this 0.15, this 15%, which is above that value. We have to use the percentage below. That should be easy to figure out because the percentage below is just 1 minus the percentage above. This is 0.15, so the percentage below is going to be 0.85. So the arguments that are used for Invnorm are first the percentage, which is in this case 0.85. Then we're supposed to put in the mean and the standard deviation. Well, since we don't know the standard deviation here, I'm not going to put in the mean of 55. I'm just going to use the standard normal distribution, which is 0 and 1. Now, this answer isn't going to be in terms of snow. This answer is going to be in terms of z-scores. So the z-score that we're looking for, the z-score that corresponds to this 60 inches, is going to be 1.036. Now keep in mind, this is not 1.036 inches. This is 1.036 as a z-score, which represents the 60. Now what we have is a z-score, which means I can use this z-score, this mean, and this x value to backwards solve to try to find my standard deviation. So we've retrieved our z-score and put it into this equation here. Now let's substitute all the other values that we know and try to find the standard deviation. And as you can see, what we did was we substituted the z, the x, and the mu, and we don't know the standard deviation, so we can solve for that. A little algebra gives us that the standard deviation is 4.83. There's your answer. Moving on to question number 17. The figure shown is the density curve of a distribution. It looks like a left-skewed curve. 5 of the 7 points make up the 5-number summary. Which 2 points are not part of the 5-number summary? So this one might seem like a doozy, but let's just figure it out. We know the 5-number summary. That's only 5 different values. It's the minimum, quartile 1, the median, quartile 3, and the maximum. The minimum and the maximum should be fairly easy to label. I know that A is probably the minimum, and G is probably the maximum. So which 2 points are not part of the 5-number summary? Well, we can eliminate anything that has A in it or G in it. So that means this one's right out. Unfortunately, nothing else has A and G in it. Oh boy. We also know that in a 5-number summary, the mean and the median have a different relationship. The mean and the median are not the same value. Since this is skewed to the left, that means the mean has been pulled to the left, but the median should be right around the middle. And by middle, that means about 50% of the data lies to the left and 50% of the data lies to the right. So if I were to choose F, that just wouldn't make any sense because this space is not as big as all the rest of the spaces. I wouldn't choose E either because this is too small of a space, even though it's very tall, to compensate for all of this. So D is going to go ahead and be the median because 50% of the data is under here and 50% of the data is under here. Now comes the slightly trickier part. I need to choose a point that it looks like 25% of the data is to the left and to the right of it as compared to A and D. So like if I chose this point B here, this little squidgen of data would represent 25%, and this large glut of data would be 25%. That doesn't make much sense. I'm going to choose C for my quartile 1. And the reason I'm choosing C is because it looks like even though this is a longer distance from A to C, which it is, about the same area is underneath the curve here because this is much taller. If I compare the area here to the area here, it looks about the same. So from here downwards, that's about 25%, and from here upwards, that's about 25%. So there's my quartile 1. So looks like I'm able to generate an answer pretty easily here. I already know that C is going to be my quartile 1, so I'm going to be able to eliminate that here and eliminate that here. I'm down to a choice between A and D, and looking this way, I'm looking for a point that splits this area into 25% and 25%. That means this way and this way is roughly 25%. It means E is my quartile 3, which means F is the wrong answer. Okay. Number 18, if the heights of American men follow a normal distribution, I'm 99.7, ooh, 99.7, I remember that number, have heights between 5 and 7 feet tall, what's your estimate of the standard deviation of the height of American men? Well, 99.7 represents plus or minus 3 standard deviations away from the mean. We know that 5 foot and 7 foot are the 3 standard deviations above and below, which means our mean is probably directly in the middle of that, which is 6 feet tall. All right, so that's the mean. What's the standard deviation? Well, I have to add 3 of that standard deviation in order to get from 6 to 7, and I have to subtract 3 of that standard deviation in order to get from 6 to 5. So from 6 feet to 5 feet, for example, that's 12 inches in between. If there's 12 inches in between and I go 3 standard deviations, that means the standard deviation is going to have to be 4. You can see a nice visual representation of it. If I go from 6 feet down to 5 feet, jumping by 3 standard deviations, I'm going down by 4 inches, down by 4 inches, and down by 4 inches. So my answer should be about 4 inches. For question 19, which of the following is not correct about a standard normal distribution? We're looking for not correct now. Remember that the standard normal distribution is the distribution with a mean of 0 and a standard deviation of 1. And there are a number of ways that you could beat around the bush with this one, but I prefer to use the calculator to compare to see if any of these numbers are totally off. The proportion of scores that satisfy between 0 and 1.5 is 0.4332. Well, we can throw that into the calculator for normal CDF. Between 0 and 1.5 should be 0.4331%. That's about right. So this is not the one that we're looking for. The proportion of scores that satisfy Z is less than 1.0 is 0.1587. So Z is less than negative 1.0. It could be anywhere from negative infinity to negative 1. That's 0.1586. Looks like that one is correct as well. Next one says we're looking for the ones that are above 2 is 0.0228. So this is all the z values that are above 2.0. That means from 2.0 to positive infinity. And 0 and 1 are the mean and standard deviation. I got 0.0227. No joy here either. For letter D, the proportion that is less than 1.5 is 0.9332. Let's check that one. Looks like I got 0.9332, which is this. We're down to the last one, so this better be right, folks. The proportion of scores that satisfy z is greater than negative 3.0 is 0.9938. Let's check it out. Phew, that was a close one. 0.9986 is not 0.9938. So this is the correct answer because it's the only proportion that is incorrect when you use normal CDF in the calculator. Questions 20 and 21 talk about the setting of SAT scores from 1995. The mean of the old scores is 470 for math, and the standard deviation is 110. In 2009, they changed it so that the mean was 515, or they didn't change it. They, the students had different scores, and the standard deviation is 116. So now we're looking for the standardized z-score for a student that scored 500 on the old SAT scale. Remember, the old SAT scale was talking about 470 and 110 being the mean and the standard deviation respectively. So we can find the z-score by just plugging it into the z formula. And the correct answer there should be 0.27. We were able to eliminate some of these, actually 3 of these already, because if the student scored 500 on that old SAT scale, the mean is 470, which means the z-score automatically has to be positive because it's higher than the mean, so it's definitely not A, B, or C. Moving on to question 21, the last and final question we're going to be talking about today. Jane took the SAT in 1994. This is the old one, and she scored 500. Her sister Colleen took the SAT in 2009, and Colleen scored 530. A little sibling rivalry here. Who did better on the exam and how can you tell? This is another Bill and George problem. We're talking about how they fared compared to their peers. If we determine the z-score for Jane and the z-score for Colleen, I suppose I should label these as z-scores, we can see that on the later SAT, that 515 is the average, and that's a lot higher than the average when Jane took it. So that should be our first indicator that something's going to go well for Jane. We got 0.272 for Jane. We did that calculation previously, and this calculation gives us 0.129, which means that Colleen did a great job, but Jane did better compared to her peers of that time. So we can go through and eliminate the incorrect ones, and whatever remains is going to be correct. It looks like Colleen did not do better because her z-score was smaller, so Colleen did not do better, and Colleen did not do better. The two sisters did not do equally well because their z-scores are not the same. It looks like regardless of whether the standard deviation was bigger, doesn't matter, we're looking at the standardized score, which is higher for Jane than it is for Colleen. This was the video on multiple choice review for Chapter 2. Good luck studying.